This presentation is about the use of SST fronts to assess upper ocean dynamics. We will see how to automatically detect SST fronts and then how to use them to assess different velocity products. First, a bit of context. We have a lot of in-situ observation available to perform current validation, such as drifters. They provide a good temporal sampling but are very sparse in space. Thus, we also want to benefit from the wealth of remote sensing observations to retrieve upper ocean dynamics information. Regarding SST, we have now three different kinds of observations: microwave low-resolution images, such as AMSR2 or GMI, infrared medium-resolution geostationary images from several sensors, for example, and we have at least one observation every hour, and finally, infrared high-resolution SST using sensor about quasi-polar satellites such as Sentinel-3 with SLSTR or VIRS, for example. The objective here is to use the gradient location of the SST image as a tracer of upper ocean dynamics. We want to compare velocity and SST image and perform a validation in terms of structure rather than pointwise. This is a good illustration of a comparison of SST fronts with velocity. On both images, we have sea surface temperature from Severi as a background. The corresponding fronts are drawn in blue. On the left image, the streamlines are derived from the velocity from globe current Siemens geostrophic current observation. We can compare the eddies detected using SST with the direction of the current and see that they mostly agree. Whereas on the right image, streamlines from Siemens Mercator model at 1/12 degree are shown, and one can clearly see a displaced eddy and some current crossing the front. Let's have a quick look at the front detection algorithm. There are three main steps for the algorithm. The first one is histogram analysis. It takes the SST image as an input, and the analysis is very similar to Kellner and Correllon algorithm. It consists of detecting population and look at the correlation of each population. Using several windows of different sizes, we can compute maps of probability of having a front. From this map and the SST image, one can perform ridgeline detection and retrieve the direction using a multidirectional operator. It uses the contrast, curvature, and homogeneity as parameters. Finally, we perform the contour following algorithm, starting with a pixel of maximum probability and detecting the next one using the direction. We loop until no pixel is found. At the end, we get fronts as vector lines, and we can apply a flagging to sort them in terms of reliability. Within the WOG project, we have used this algorithm to process data for two different regions and using two different SST observations on a 10 years period. We have data from several sensors for the high resolution and microwave level 4 RENS product for the low resolution. The two regions are the Agulhas area and the North Atlantic. A link is provided on the poster to download data. Now we will see how we can use this front to compare front and velocity. First, we consider that tracer front represent a barrier of transport, and that the current should not cross the front. The metric consists of computing the difference of angle between the direction of the front and the direction of the current. The smaller the metric, the better the adequation of the current with the SST observation. Here we are analyzing three different products. From left to right, we are looking at data from the WOG BFN geostrophic current, the globe current Siemens geostrophic current, and the Mercator Siemens model at 1/12 degree. The sea surface temperature from Severi has been used as a background image. The metrics are plotted on the front lines in color with blue for low metric value, so good agreement, and red for high values, so bad agreement. Looking at the highlighted areas in the black circles, one can see that the structures in the first product are in better agreement as the metrics are in blue and correspond to low value. On the contrary, in the right image, the current is crossing the fronts at many places, and thus the metric shows high values in red. In the middle, globe current velocities are globally following the fronts, but we can see that some sharp turns are missed and they lack in spatial resolution. Clicking on each image in the poster will bring you to the work visualization portal so that you can browse more data. To rank different velocity products, we can compute statistics of the metrics on temporal and spatial box. The size of the box depends on the analysis we want to do and the number of data points available. For example, 2 by 2 degree box with 3 to 7 days analysis work well for near real-time assessment, but one can look at longer periods to get an overview of the performance, or look at the seasonality. In each box, we can compute different statistics such as the mean values of the metric, the ranking of the different velocities, and differences between two different currents. We show here the mean ranking on a 5-day window for 3 velocity products shown before. The ranking values are ranging between 1, first, for the best product in blue, and third, so last, in red, for the product with the worst agreement. As expected from the visual inspection we did before, the work BFN, so first product on the left, shows the best ranking in blue, and Mercator model differs the most from the front. Let's talk now about the pros and the limitations. The method has been used to assess and intercompare a wide variety of velocity products. It is interesting as using geostationary satellite, we can perform statistics on many validation points, and we can play with the resolution for the box. Near real-time analysis can be done with a significant amount of validation points. Also, the position of the structure is validated more than a RMS value, which is of interest in many cases where we need the location of the eddy or the front rather than the value, such as it is the case for the ship routing. Of course, it has also some limitations. The first one is that the quality of the frontal detection is essential to get a reliable analysis. Also, only relative comparison between different sources have been done so far. One should be careful also to check that the advection component is small enough, using, for example, front tracking analysis, as we neglect this component in our analysis. At last, the strength of the current is not measured here. So to conclude, in this poster, we have shown the benefit of using frontal structures from SST images to assess upper ocean dynamics. It has been applied on several cases, such as for optimizing velocity reconstruction algorithm, or operationally to choose the best forecast for ship routing. There are still some studies to fully characterize the method that needs to be done. First, we want to calibrate the method better using a model. Then, look at higher resolution SST will reveal limitation of comparing the SST and the velocity. And at last, we also want to detect front from chlorophyll concentration products and look at how they compare with the velocity and the SST fronts.